Hi, I'm Mark Barsamian. In this video, I'll be discussing divisibility, which is in section 4.4 of the book. Before starting, let's review what we've been doing so far in this chapter. We've been discussing proof structures, so we've talked about how you prove existential statements true by giving an example. You disprove false universal statements by giving an example. A universal statement with a finite domain that is a true statement can be proven by what's called the method of exhaustion, which amounts to a bunch of examples. But universal statements with an infinite domain that are true have to be proven by the harder method of generalizing from the generic particular, that is, not by an example. And an existential statement that is got an infinite domain and that is false, it will have a negation that's a universal statement. And so if you are going to disprove the original existential statement, that means that you have to prove the negation that's a universal statement. And so that will require the method of generalizing from the generic particular. And there's some more terminology. If you apply that method of generalizing from the generic particular to the special case of a universal conditional statement that has an infinite domain, then that resulting proof structure is called the method of direct proof. And we've studied proofs and written proofs that involve a growing list of defined mathematical terms. So we've had even and odd numbers, composite and prime numbers, consecutive integers, rational numbers and irrational numbers, and we've had the zero product property. In this section 4.4, we won't learn any new proof structures, but we will add to our list of defined mathematical terms and mathematical concepts. The new mathematical term is divisibility, and the new mathematical concept is prime factorization. So we'll start with divisibility. The definition of divisibility is as follows. There's this new symbol. It's a D and then a little vertical bar and then an N. And this is spoken D divides N. It's also spoken D is a divisor of N. And it's also spoken N is divisible by D. What does it mean? Well, here's the meaning in words. It means that the letter N and the letter D both represent integers, and that this is an integer. N divided by D is an integer. If I want to express what I just said in words, in symbols, it would be written this way. N and D are elements of the integers, and there exists an integer k such that N divided by D is k. Now, it is possible to express the meaning of divisibility using just multiplication, not the idea of division. Here's the idea. We're going to replace this existential statement with a different one. Now, part of what we're going to replace it with is this expression, which just involves multiplication. It says N equals D times K. Now, this expression up here says N divided by D equals K. You might think at first glance that those two things are comparable, but you realize that in this expression, for that expression to be true, D cannot be 0. Whereas on the bottom line, this expression could be true when D is 0. So we need to add a requirement on the bottom line that requires that D is not allowed to be 0. That's what that term is there for. So the blue circled expression can never be true when D is 0, and this great big green circled expression can never be true when D is 0. Let's do an example. Does 13 divide 91? Now, what does that mean? Let's go back up and look. 13 vertical bar 91 would mean that 91 divided by 13 is an integer. So this certainly seems true, but to confirm that it's true, you really have to give the integer that makes it work. So the answer is yes. So that's confirming that the answer is yes, using the idea of division. Now let's explain a different way. So we have two different styles of explanations. One involves the idea of division, and we had to name the integer. The integer was the number 7. We had to come up with the example of the integer that works. The other explanation was this one, which does not use the idea of division. It only uses the idea of multiplication. So to explain things this way, we have to hit the reader over the head and say the thing that's playing the role of the letter D is not 0. And then we still have to provide the integer that makes the whole thing work. The integer is 7. Related question is this one. Does 91 vertical bar 13? Explain. So how would we speak this? Well, the question is, does 91 divide 13? And we can ask this question a different way. That is, the question could be rephrased, is 13 divided by 91 an integer? And the answer is no. Let's go on and do another example. Example 2. So this question A is, does 13 divide 0? Well, another way of asking this question is 0 over 13 an integer? Well, we can see that the answer is yes. Now I'm going to color code my explanation. I changed colors midway through that line. The reason is there's often some confusion when you have the number 0 in sentences involving divisibility. There are two zeros in this expression. One is the 0 that we were given. It was this blue 0, and it goes into the top of this fraction. The other is the 0 that we came up with to show that the whole thing works. So we came up with that red 0. We did not come up with the blue 0. They came from different places. So this whole explanation here involves division. We can also explain using multiplication. So the explanation is, the answer is yes, and it's because 0 equals 13 times 0. And notice that I've color-coded this, and I've actually said some more words beyond what I just spoke just then. The explanation is yes, because 0 equals 13 times 0, where 0 is an integer. Now you might see a little more clearly why I think the color coding is useful. Again, in this green sentence, the blue 0 and the blue 13 were the numbers that were served to us in this original question. They show up down here in blue. My explanation of why this is the answer to this is yes, my explanation involved coming up with this red number 0. So the two zeros in this bottom equation came from different places. The blue one came from the numbers that we were given in the question. The red one came from my explanation in my answer. Now, I've actually forgotten something in my explanation. I also have to add, my explanation has to include the phrase that 13 is not equal to 0, because in the definition of divisibility, the one that involves just multiplication, you have to confirm that both of those things are true. So we did this. We said that our red number 0 was an integer, but we did not say that our blue number 13 was not 0 until I remembered to tack it on there at the very end. Okay, let's go on to question B. Does 0 divide 13? Well, the answer is no. Let me put a little divider here to separate these questions. The answer is no. I'm going to give two explanations. One explanation is going to involve division. So this explanation is in the language of our first way of defining divisibility. This way. To say that d does divide n means that n divided by d is an integer. So if this is not true, that means that that symbol is not true. Now, I can also have an explanation involving multiplication. And that can just simply be because d equals 0. So our answer is no, and the reason is because d equals 0. That explanation refers to the second way of defining divisible. The second way of defining divisible is this sentence. Notice for d to divide n, or for n to be divisible by d, all of this stuff has to be true. So in particular, d has to not be 0. So if you have a value of d, if you have a number that's sitting here on the left side of that vertical bar, and it fails that test, then the whole thing fails. Let's do another example. Suppose that n is an integer. Is this quantity divisible by 35? And explain. Well, the answer is yes, but we have to find a k that works. So our explanation is in the form of showing that this thing can be written as 35 times some integer, where and we have to come up with the integer. And we also have to say that 35 is not 0. Let's do another example. Consider this statement. If AB divides C, then A divides C and B divides C. So the first question is to rewrite that statement formally. Notice that this is implicitly quantified. Well, that statement is actually true. So how are we going to prove it? Well, notice that it's a universal statement, and the domain is infinite. In fact, it's a universal conditional statement. So that tells us that we need a proof structure that is called direct proof. So I'm going to put a copy of that statement that we're going to be proving on the next page, and we'll do our direct proof there. So there's the statement that we need to prove. So remember the direct proof structure. We have a frame. In question 1, we introduce elements that are generic, particular elements of the domain that have the qualifications mentioned in the hypothesis. That's the first part of the direct proof structure. The second thing we get from the direct proof structure is the way the proof has to end. So in this direct proof structure, Again, the generic particular element that satisfies the requirements described in the description of the domain and on the hypothesis, that generic particular element, or the three of them, show up in the very first statement. And the very last statement of the proof is just the statement of whatever is in the conclusion. This stuff on the last statement of the proof came right from the then part in this statement that we're trying to prove. So there's our direct proof structure. Now, remember what we've done before. We've thought about what else can we fill in this proof structure. Notice that this is a defined term. So we have no choice about how we're going to have to proceed. The next statement is going to have to be a statement in which we unpack that definition or that defined term. So there's our unpacking of that defined statement. To say that AB divides C means all this stuff. Notice that I included the idea that AB has to not be 0. Now let's look forward to the end of the proof. The end of the proof is that red circled statement that includes two defined terms, or includes a defined term used twice. So there's no choice about how we're going to have to end this proof. Before we can state this last line, we're going to have previously stated two things. So that red statement that I've written is what it means to say that A divides C. And so, in fact, not only do we know that that red statement is going to have to be there, we know that in the last statement of the proof, the justification is going to have to be, well, here, I'll write it. So that red statement at the end, A divides C, has to be preceded by this circled red statement. There's more in the last statement of the proof. There's this. That's a defined term. We can't state that unless we have previously stated this. So these words that I just wrote in black mean the same thing as this. So in the last statement, the justification is going to include this. So there's our proof structure provided by direct proof structure, and provided by the idea that when we use a defined term in a proof, it has to be used in a certain way. So this green step 2 was necessary to unpack that definition. And these two lines at the end, the black and the red lines, are necessary so that in the very last line we could pack up those definitions. Notice one more thing. The definition of divides mentions the letter K. In my starting of this proof, I used the letter K. There, on line 2. So K is used up. So in later steps, I did not use the letter K. I had to introduce other letters. All right, now how can we fill this gap? Well, look forward to where we need to go. We need to have an equation that says this. C equals B times N. Well, hey, look backwards. We know that that circled equation up there is true. We also need to know that B is not 0. Hey, look back. We know that AB is not 0. So we can get what we need for this black statement here just by looking back at this green statement and making some observations. One thing that's going to be helpful to have observed is that neither A nor B is 0, because we know that the product is not 0. We'll use the zero product property to say that. So notice we need to be able to say that B is not 0 in that black statement near the bottom of the proof. And we've now said B is not 0. And that's because we knew that AB is not 0. Now the other thing that we need to be able to say is that C equals B times N. But look, we know this equation is true. So that gives us an idea of what to use for our letter N. So if I introduce this value for N here, I need to say a couple of things. I need to point out that N is an integer, and I need to point out that C equals B times N. So now look ahead to our black statement. We've now got all the pieces that we need to make that black statement. That black statement is by statements 3 and 4. Okay, so we've taken care of this black statement. It's got all it needs. Now for the red statement, we need to have two things. We need to have A not be 0. Okay, we've got that. That's taken care of. And we need to have this satisfied. Well, let's look back. We know that this circled equation is true, and so that should be able to give us this. But we have to know of something that can play the role of M. So we have to introduce our M. So there's our M. It's this BK, and we observed that M is an integer and that C can be written as AM. So now look ahead to the red statement. We need to be able to say that A is not 0. Okay, we've got that. That's in step 3. And we need to be able to say that M is an integer. Okay, we've got that. That's there. And we need to be able to say that C is equal to AM. Oh, that's there. So all the things we need to justify that red statement are in statements 3 and 5. So look, we are ready. We've closed the gap. We are now ready to number our previously unnumbered statements. The black statement is going to be statement 6, and the red statement is going to be statement 7, and the very last statement of the proof is going to be statement 8. So the chronology, again, is that we use the direct proof structure to know that we had to have that frame, and then we use the idea of how you have to use definitions in a proof to know that we had to have the statements with the star in front of them. Statement 2, statement 6, and statement 7. Of course, we didn't know the numbers of those statements. So the only thing that we had to come up with was this chewy center. We had to figure out how to bridge the gap in that proof. That's the end of that example. Let's go on to the next. This example has a typo in it. This should say A divides C. So we have to rewrite this statement formally. If A divides BC, then A divides B, and A divides C. Now, what's not formal about that? Well, what's not formal about it is that it's implicitly quantified. So writing the statement formally means we've got to figure out what the quantifiers are and state them clearly. Quantifiers with domains. So for all A, B, and C that are integers, if A divides BC, then A divides B and A divides C. Now, question B, we have to prove or disprove that statement. Well, notice that this statement looks a lot like the one that we just proved in statement 4. In example 4, we proved this. If AB divides C, then A divides C and B divides C. Very similar looking statement. But it turns out that this statement is false. So we have to disprove it. Now this is a universal statement, so to disprove it we have to give an example that shows that it's false. I'm going to name this statement. Statement S is that universal statement. It's a universal conditional statement. So to disprove statement S, we have to come up with a counterexample. That is, we have to give an example of an A, B, and C that makes the negation of S true. Well, for that, it'll be helpful to write what the negation of S is. Now, I'm just going to write down the result of the negation of S. Notice that S is a universal conditional statement. So we know that when we negate a universal statement, we're going to get an existential statement. We know that when we negate an if-then predicate, it's going to be a new predicate that's an and statement, not another if-then. Furthermore, we know that when we negate this, it's going to be an or statement. So there I applied my rules of negating. I did all that in my head. So we're looking for an A, B, and C that are integers such that A does divide BC. And either A doesn't divide B or A doesn't divide C, or maybe both. Well, I'm just going to suggest an example. So if we let A, B, and C be the numbers 6, 4, and 3, observe that 6 does divide 4 times 3, because 4 times 3 is 12, and that can be written as 6 times the number 2. So we had to come up with this 2. So we have demonstrated that A does divide BC. But the sentence A divides B is false. That is, 4 divided by 6 is not an integer. So since 6 divides 4 is false, we can write this simple. That is, A does not divide B. Also notice that 6 divides 3 is false, because 3 divided by 6 is not an integer. So we'd say that 6 does not divide 3. So A does not divide C. So we've come up with an example of ABC such that A does divide BC, but A does not divide B, and actually A does not divide C either. So we have come up with an example, and we've explained clearly why that example works as a counterexample. So again, our job was to come up with a counterexample and explain to the reader why it works as a counterexample. Now I want to do some examples that involve the new term divisibility and previously defined terms. So the first example involves divisibility and even numbers. So here's the statement we want to consider. The product of any two even integers is a multiple of 4. So our first job is to write that statement formally. To rewrite this statement formally, it helps to sort of go in stages. For all even integers m and n, the product mn is a multiple of 4. So there's the predicate. But notice that predicate involves this expression, which is a defined expression. We really should quantify this, show how it works with quantifiers. So there is the same predicate, just written using quantifiers. So notice we've sort of, in the job of writing the statement formally, we've also unpacked that definition. we've written what it means to say that something is a multiple of 4. So we no longer have that term multiple of. We just have this phrase which means the same thing. So there's our statement. We need to prove or disprove that. Do we believe that this statement is true? The product of any two even integers is a multiple of 4. Well, yeah, it seems to be believable. I mean, 6 is even, 14 is even. 6 times 14 would be 84. That's even, and so forth. But we can't use an example to prove it. We have to do a general proof. Well, let's do the proof right here. We're going to generalize from the generic particular example. So that means we have to start by introducing generic elements of the domain. That's how the proof has to start. And how does the proof have to end? We have to end by having that as our last statement. So there's our frame. We have no choice about how this proof has to start. It's got to start with that statement. And we have no choice about how this proof has to end. It has to end with that statement. That statement, the ending, came from there. And this statement is a generic particular example of elements from that domain. So this proof structure is generalizing from the generic particular element. We have no choice about this frame. Now, look what else we have no choice about. The first statement involves a defined term. So we have to unpack that defined term. So statement 2, there exists an integer j such that m is equal to 2j. That's just by statement 1 and the definition of even. So we've unpacked that defined term. Now we have another sentence just like that for the letter n. So statement 3 is unpacking the knowledge that n is an even number. N is even means there exists an integer p such that n equals 2p. Now notice, the definition of even in the very beginning when we first started talking about even numbers, and a number is even if it can be written as 2k for some integer k. But I didn't use the integer k. I used the integer j in statement 2 because k was already used up. I had already used the letter k in that last statement. And then when I came to statement 3, I couldn't use j or k. I also couldn't use m or n because they've been used. I had to come up with some other letter that could play the role of my integer. Okay, so we have no choice about the frame of this proof. It comes from the method of generalizing from the generic particular element. And we have no choice about these two statements. They need to be there because we have to unpack this defined term that was used in statement 1. So we have this little gap to bridge now. We have to get from statements 1, 2, 3 down to here. We're heading for this. We would like to have this equation be true. Well, look, we don't have our k yet, but we have our m and our n. We know what they are, so let's just build the left side of that equation and see where it takes us. M times n is 2j times 2p. Oh, but that's easy. That can be rewritten as 4 times jp. Now I'm going to have to squeeze in, maybe I'll just make some room by moving this last statement down. Okay, so now I've got room for a statement to be squeezed in here. So looking forward, we knew that we were trying to find a k that worked. So I've introduced it. So in our last statement of the proof we now can number. That's going to be statement 6. And the justification for this is going to be by statement 5. And that's the end of the proof. Let's go on to another example. Example involving divisibility and consecutive integers. So this statement, the sum of any 3 consecutive integers is a multiple of 3. Well, that's the statement we're interested in. First question is rewrite that statement formally. Now, we need to write this formally. That means with variables and quantifiers and domains. Now, you might think that to describe 3 consecutive integers, we might need 3 letters, like maybe ABC or JKL or something like that. But remember that 3 consecutive integers can always be written in the following way. Any 3 consecutive integers can always be written as m plus 1, and m plus 2. So if you want to describe any 3 consecutive integers, you really only have to give the value of m, the lowest of the 3. So my quantified statement can look like this. There's my quantified statement. That's the formal version of the statement that was written above as a sentence. So how do we prove or disprove this? Well, this statement is actually true, and it's very easy to prove. So I'm just going to jump to the proof. The proof structure is going to be generalizing from the generic particular element. So we're going to have to, in statement 1, introduce a generic particular element, one that is an element of that domain. So we have no choice about how that proof has to begin. And we have no choice about how the proof has to end. The proof has to end with the statement that is in the predicate. So that frame is the frame we get with the method of proof called generalizing from the generic particular element. Now, what else can we fill in here that's inevitable? Well, what's inevitable is that we have to deal with this defined term. So before we can have this last statement, we're going to have previously stated this. So we have to have that statement before the last statement. And furthermore, we know that the justification for the final statement is going to be by the previous statement. And the definition of the words is a multiple of. All right, so that's another part of our proof structure that we have no choice about. So our gap is this little bit to get from statement 1 to that green statement. Well, look, the green statement includes a left side that we can just build. So let's go back to the beginning, work our way forward by just building this quantity. Well, look, that quantity simplifies to just simply 3m plus 3. And look how close we are to what we need. We need to have something of the form 3k. So let's go one more step and factor that. So we're almost there. We need to have 3k. What we have is 3 times the quantity m plus 1. So now it's clear what we should do. We should introduce our k. Now we have to introduce our k and be clear that we know that k is an integer. It's because m is an integer. We're now ready to number our green statement. Our green statement's going to have to be statement 4, and we're ready to number the final statement of the proof as well. The justification for statement 4 is by 2 and 3, and the justification for statement 5 is by statement 4. All right, that's the end of that proof. Let's go on. Now I want to talk about what's called the unique factorization theorem. In the book, it's this theorem 4.4.5. I'm actually presenting the version of the theorem that includes a couple of things that are outside of the theorem in the book. The theorem in the book's presentation does not include mention of the standard factored form, but the book shows the standard factored form right after the theorem, so I just decided to combine them into one thing. I've got a typo here. This should say factored. So here's what the theorem says. Given any integer n that's greater than 1, there exist three things. There's a positive integer k. There's a list of prime numbers, k of them, starting with one called p subscript 1, ending with the one called p subscript k. A bunch of prime numbers in increasing order. I've got them listed in increasing order. And furthermore, there's a list of positive integers. So these are integers, they're called e subscript 1 all the way up to e subscript k. So there's a list of k prime numbers, and there's a list of k integers called e. So we've got three things. We've got this integer k, we've got this list of prime numbers, and we've got this list of integers. Now, what about them? They have the property that n can be written this way. N can be written as a product of terms, each of which is one of those prime numbers raised to the power of one of those integers. And that's called the standard factored form of n. This expression is called the standard factored form of n. We're just going to do some examples. So for example 8, n is this number, 428,064. Find the unique factorization of n. Well, I'm just going to skip to the results here. You all have, at some point in your pasts, learned about how to find factorizations. The book describes this some, but it's prerequisite for this course. So there's our prime factorization. Notice a couple of things. What's our k? Our k is the number 4, because there are 4 primes involved in this factorization. We have p1, prime number 1 is the number 2. Prime number 2 is the number 3. The prime number 3 is the number 7. And finally, the last prime in the list is prime number 4, p subscript 4, and that's the number 13. So there's our p1, and there's our pk, a list of 4 prime numbers. And what about our e's? Well, the e's are the exponents. Exponent 1 is the number 5. So the exponents are the numbers 5, 1, 3, and 1, but they're given the names E1, E2, E3, E4. All right, so there's the prime factorization. Question B, write the prime factorization for n cubed. Well, n cubed is written that way, most simply, but that's not presented as a prime factorization. There's the prime factorization. I multiplied each of those exponents by the number 3. 3 times 5 is 15. 3 times 1 is 3. 3 times 3 is 9. And 3 times 1 is 3. Notice that when you cube a number, all of the exponents in the prime factorization are multiples of 3. That's going to come up in this next question. What's the least positive integer m so that nm is a perfect cube? Well, that means that in the prime factorization for nm, all of the exponents are going to have to be multiples of 3. So we need to prime factorization for nm that has all exponents that are multiples of 3. Okay, well this seems kind of vague, doesn't it? But let's start by writing down what that's going to look like. So nm is going to look like that. We know that n can be written this way, and then whatever is going on with m is out here. So when I multiply these together, I'm going to have to address the fact that I've got some exponents here that are not multiples of 3. I've got 2 to the 5th, I've got 3 to the 1, and I've got 13 to the 1. So in order for this product to be a perfect cube, I'm going to need to have some extra factors of 2 and 3 and 13. So the factorization of m needs to include at least 2 to the 1, because that will get together with this 2 to the 5th, and that'll give me 2 to the 6th, and 6 is a multiple of 3. The factorization of m needs to include at least 3 squared, because that 3 squared will get together with that 3, and that'll give me a 3 cubed, and the 3 in the exponent is a multiple of 3. And I need to have a 13 squared, because that 13 squared is going to need to multiply that 13 to give me 13 cubed, so that I have an exponent that is a multiple of 3. Now, the factorization of m might have some other stuff in it as well, but wait a second, we want the least positive integer m. So let's have our positive integer m be the integer that just includes that stuff. So the idea is, let m be that stuff. Now, what number is that? That's 3042. So we see that it does work. When I let m be this number, then nm is this thing, which is a perfect cube. Now, the question D says to write that number as a perfect cube. Well, what is that number? I don't really want to do that number, but I'm going to just for fun. With a computer, I can find this out. This is 1,302,170,688. But that's not what the job was. The job was to write that as a perfect cube. There's the factorization rewritten as a cube. So what is that number in parentheses? That's 1092 cubed. So nm can be written a bunch of different ways. Here's the prime factorization for nm. Here is the number nm. And here is the number nm written as the cube of a number. We have one more example. This example says, let n equal 17 factorial. Write n in standard factored form. All right. Well, let's just start by writing out 17 factorial and then write out its factors. So there's 17 factorial. Now let's factor these things. So there is the same list of numbers, but each one presented in its prime factorization form. So this is the prime factorization of 12. And this is the prime factorization of 15. Well, we can gather up terms. So let's start with the lowest prime. Do we have to write this in its standard factored form? So we have to start with the lowest prime, 2. So how many powers of 2 do we have? I've got 4 there, another one that makes 5, 2 more that makes 7, another one that makes 8, 3 more that makes 11, another one that makes 12, 2 more that makes 14, another one that makes 15. So the power of 2 in the factorization is 15. Now let's see, we have the number 3 in the prime factorization. How about the exponents for the number 3? Well, let's see. There's 1 there. There's 1 more there that gives us 2. There's 3 more that gives us 5. There's 1 more that gives us 6. And there's 1 more that gives us 7. So 3 to the 7th. Okay, now we have the number 5 in the prime factorization. How many powers of 5 do we need? Well, there's 1 there. There's another one there. And there's another one there. So there are 3 powers of 5. Or 3 factors of 5. Let's see, another prime in our list is the number 7. How many of those do we have? Well, let's see. We have a 7 there, and we have a 7 there, and those are the only 7s that we have. So we have 7 squared in our factorization. And the next prime is 11. How many 11s do we have? Just 1. Okay, the next prime that appears is the number 13. It appears as just 13 to the first power. And the next prime that appears is the number 17. So there's our prime factorization, our standard factored form for n. So here's a question. Question B. Without computing the value of n cubed, determine how many zeros are at the end of n cubed when it's written in standard decimal form. Yikes, how do we do this? Well, we're told to not compute the value of n cubed, but we can write the standard factored form of n cubed. So n cubed is going to be all that stuff cubed, so that means that each of the exponents gets multiplied by 3. Okay, so there's the prime factorization for n cubed. Now the question is, how many zeros will be at the end of n cubed when it's written in decimal form? Well, remember that the only way to get a 0 at the end of the decimal form of a number is to have 10 be a factor. If there's 1 0 at the end, then 10 is a factor of your number. If there are 5 zeros at the end, that means that 10,000 is a factor. So each 0 at the end comes from there being a factor of 10 in the factorization. Oh, but wait, each factor of 10 is a factor of 2 and a factor of 5. So each 0 at the end of the decimal form of n cubed will come from something of this form, 2 times 5, that is a factor of 10, in the prime factorization of n cubed. Okay, well, the question is, how many of these things can we build from this prime factorization? Well, we have to think about how many 2s and 5s we have. We got a whole bunch of 2s. We got 45 2s, but we only have 9 factors of 5. So we can put this a different way. So n cubed could be rearranged into a presentation that's not the standard factored form. We could put all the factors of 2 and 5 up front. And then all the other stuff is a bunch of factors that don't involve 2 or 5. So the red stuff is going to be an integer that is not divisible by 2 or 5. So that red stuff is going to be a number that is not going to have any zeros at the end of it. So any zeros at the end of n cubed are going to come from it having this. Well, let's rewrite this some more. So we broke off some of the 2's, and so now we've got this sitting in front. 2 to the 9th times 5 to the 9th times all this stuff. So all that red stuff doesn't have any 5's in it, so that red stuff is not divisible by 10. We can write this again. So when I think about rearranging the factors of n cubed, I realize that I can rewrite n cubed as something that has 10 to the 9th times some red integer that does not have 5 as a factor. So the only thing that could be contributing to zeros at the end of n cubed, the only thing that could be contributing to that is this 10 to the 9th. So that tells us that there are going to be 9 zeros on the end of n cubed. And so that's our final answer. There will be 9 zeros at the end of n cubed. So that's the end of that example, and that's the end of the video. Thank you.